Testing for real. 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 Testing for real.
I didn't even ask.
Testing for real. Testing for real.
I'm not hearing anything on Zoom.
What?
I'm not hearing anything on Zoom.
Huh, that's bad. I didn't even ask.
Testing for real. Testing for real.
So it's not. So you don't hear me from now. No. No, that's bad.
Huh, that's bad.
Testing for real. Testing for real.
So it's not.
I mean,
so you don't
here
hear
it
me
looks like
from now. No.
it's
No, that's bad.
It looks like the microphone
Testing for real. Testing for real.
So
we
it's
can
not.
try
So
this
you don't
here.
hear
It
me
looks like
from now. No. No, that's
again,
bad.
it looks like the microphone
Testing for real. Testing for real.
So
we
it's
can
not.
try
So
this
you don't
here.
hear
It
me
looks
from
like
now. No. No, that's
again,
bad.
it looks like the Okay. Is it what?
I think so.
Okay. Is it what?
I think so.
Did you have the photocopy? I don't know because I was not able with the computer. I asked one. Did you have the photocopy? Can you bring also the cleaner for the whiteboard? There is like a spray one. Some of the whiteboard has like spray. Did you have the photocopy? Can you bring also the cleaner for the whiteboard? There is like a spray one. Some of the whiteboard has like spray. Did you have the photocopy? Can you bring also the cleaner for the whiteboard? There is like a spray one. Some of the whiteboard has like spray. You have this. Did you have the photocopy? Anybody? Can you bring also the cleaner for the whiteboard? There is like a spray one. Some of the whiteboard has like spray. You have this.
I don't know where one.
Anybody? Can you bring also the cleaner for the
I think the guy, as long as you don't mind.
some of the whiteboard has like spray.
I don't know where one.
Anybody?
I think the guy, as long as you don't mind. I don't know where one. I think the guy, as long as you don't mind. I don't know where one.
Okay.
I think the guy, as long as you don't mind. I don't know where one.
Okay.
I think the guy, as long as you don't mind. I don't know where one.
Okay.
I think the guy, as long as you don't mind. I don't know where one.
Okay.
I think the guy, as long as you don't mind. I don't know where one.
Okay.
I think the guy, as long as you don't mind. I don't know where one.
Okay.
I think the guy, as long as you don't mind. I don't know where one.
Okay. In case you could check.
Oh, okay. That's good to know, but I'm probably going to be so distracted. It's not going to occur to me. Thanks. Thanks, Albert.
In case you could check.
Oh, okay. That's good to know, but I'm probably going to be so distracted. It's not going to occur to me. Thanks. Oh, that's perfect. Thanks, Albert.
In case you could check.
Oh, okay. That's good to know, but I'm probably going to be so distracted. It's not There's like an organization. So there's.
In case you could check.
Oh, okay. That's good to know, but I'm probably gonna be so distracted. There's like an organization. So there's.
In case you could check.
Oh, okay. That's good to know, but I'm probably gonna be so distracted. There's like an organization. So there's.
In case you could check.
Oh, okay. That's good to know, but I'm probably gonna be so distracted. There's like an organization. So there's.
Give them just a couple of minutes. We are missing people here and online.
That's good to know, but I'm probably gonna be so distracted.
Give them just a couple of minutes. We are missing people here and online.
That's good to know, but I'm probably gonna be so distracted.
Give them just a couple of minutes. We are missing people here and online.
That's good to know, but I'm probably gonna be so distracted.
Give them just a couple of minutes. We are missing people here and online.
That's good to know, but I'm probably gonna be so distracted.
I wouldn't say it was a lot of, yeah, we had a little bit of name following. We talked about one written. I wouldn't say it was a lot of, yeah, we had a little bit of name following. We talked about one written. Right. I wouldn't say it was a lot of, yeah, we had a little bit of name following. We talked about one written. Right. I wouldn't say it was a lot of, yeah, we had a little bit of name following. We talked about one written. Right. I would say a lot of this, yeah, we got something. One group of right. I would say a lot of this, yeah, we got something. One group of right. I would say a lot of this, yeah, we got something.
Okay,
I'm hearing it repeat, and I don't know if it's on.
like test, like that.
I guess maybe it was.
That feedback.
Sounds good.
Okay. So, what do you think of that? Can we go? Yeah. Okay. I think we are almost everybody. So welcome everybody for the second day of HUGS. We will have the second lecture on Introduction to QCD and Small X Physics now with Matt Sievert. Just a brief reminder to the online students. If you raise your hand, we give you the right to speak, and so you can ask the question. And if you turn on the camera, Matt can see also your face on the video, so on the TV. So please go ahead, don't be shy, also online, and ask questions. Excellent. Let's do you.
Okay, good morning, folks. Is the audio coming through okay? Excellent. Okay, before I dive on in, I just wanted to point to how I'm uploading things on Indico. As yesterday very clearly illustrated, my guess of where one lecture ends and the next begins is not quite calibrated yet. So what I'm doing for now is I'm just continuing to upload all of the lectures as I go, and then I'll try and split them up separately into individual PDFs afterwards. So for now, for today, I've uploaded a combined lecture 1 through 3. You can again get that through the Indico page, and that now includes the stuff that we covered yesterday, which now has a section break where we actually stopped, and I'm going to continue trying to split things up as we go along. The other thing that I wanted to point out is in the full PDF versions of the notes, there's various other things that might be helpful for you, like these hyperlinks to appropriate sources for more information. So there's other things in here beyond what we actually get to cover on the board today. Okay. So let me go to the board and recap where we were last time. So last time I tried to sort of start at a very high level and orient us about how we're going to approach QCD. My goal is to derive or construct the QCD Lagrangian, hopefully within the next 2 hours or so, that tries to really explain what does it mean, where does it come from? What does it mean when we say that QCD is the gauge theory of SU3 symmetry? So last time we started off with sort of a you are here map of the mall, saying if we're interested in QCD, QCD is a very unique non-abelian gauge theory. Gauge theories are a unique subset of interacting theories, and the entire framework that we're working with is a relativistic quantum field theory, which is the ideal marriage of relativity and quantum mechanics. Before diving into all of the details, we started off with a discussion about what one can and cannot learn from perturbation theory. Perturbation theory is great because it's a systematic expansion, unlike, say, density functional theory, where you have the ability to calculate something, but you don't know how big your error is. Perturbation theory is sort of always controlled in this way. But it's not complete. There can be non-analytic functions, and we talked about an example last time, that simply don't have a Taylor series that we cover. They cannot be expanded. So if you work only in perturbation theory, you will never see such functions by construction. Even when perturbation theory is working, it doesn't necessarily converge, even though we often pretend that it does. So just working to higher and higher orders is not necessarily always a good idea. But perturbation theory can tell you how its degrees of freedom are evolving as long as they evolve slowly enough and they're not radically ruptured by a phase transition or something. This is what goes under the heading of resummation. And that is what we are aiming for ultimately as far as the low X side of things, to derive what is the resummation of low X physics and how does that change your cross sections. So then moving towards this discussion of gauge theory, the original sin, the problem of all of this, is the existence of the scalar polarized mode for a vector field. Vector fields are allowed to have up to 4 polarizations, 3 space-like, 1 time-like, and that time-like polarization, since it's related to the metric tensor, comes in with a different minus sign than the space-like ones. So if the space-like polarizations are well-behaved, the time-like polarization is not, and that leads to negative definite quantum states, which is not compatible with any quantum theory, quantum states that live in the Hilbert space. And we talked about the way that a gauge theory elegantly solves this problem. If you have a massive vector boson, then I guess you can just get by with a constrained quantization, which is hard but doable. But a gauge theory solves this problem in a really beautiful way if the interaction of your vector field to anything else in the Lagrangian is of this very particular form, J dot A, where J is a conserved current. Then the transformation of A by shifting it with a scalar polarized mode is exactly equivalent to just adding a total derivative to the Lagrangian. And that's not an observable shift, right? That's a symmetry of the equations of motion. So this kind of interaction is very special. This one allows you to sweep this scalar polarization under the rug and turn it into an unobservable symmetry transformation instead. And so this is sort of the standard lore about gauge transformations being redundant degrees of freedom. That is not an accident, that is intentional to get rid of these scalar polarizations in the most effective way possible. So that was where we left off. So now let's talk a little bit more about what constructing this gauge structure actually does for our theory. So we started off with the free Dirac Lagrangian, which was for QED psi bar I d slash minus n psi. Here I only need one kind of fermion. We'll worry about multiple colors or multiple quantum numbers in a few minutes. So the free Dirac Lagrangian was this. We added a term of the form minus E psi bar gamma mu psi a mu to it. And that produced the, well, I don't know, let me call this the gauged Lagrangian for the moment. It's not completely QED because it doesn't have the kinetic term yet, but it does accomplish adding this special interaction form that renders this piece gauge invariant. So the addition of this extra term actually falls very nicely into the same structure as the free term that we had before. This d slash, as you recall, is just the contraction of the gamma matrices gamma mu with the partial derivative. If I've got the psi bar gamma mu psi here, that nicely combines with this structure. So this suggests that adding this extra term is almost like redefining the partial derivative. So if I just group these terms, everybody has a psi bar, everybody has a psi, everybody has a I gamma mu in this first term. And then the original Lagrangian we had has a partial derivative. And if I've got a minus sign here and I pull out an I, then I get plus I e a mu minus n psi. Yes, very good. This object is, as I said, a modification of the partial derivative. This is referred to as the gauge covariant derivative. So this is capital D mu. And so the gauge Lagrangian, after adding this term, you can write it as just a mapping of the partial derivative to the covariant derivative. So in a very simple way, minimal coupling, the addition of this extra term of this form, can be thought of as just the replacement of the partial derivative by the covariant derivative, which introduces the vector field in exactly the right way that it produces this J dot A form. Okay, so what does this do for us? When we've added this particular form, now this effectively enlarges the symmetry group of our Lagrangian. We started off with the free Lagrangian, which was invariant under only global U1 transformations. Global U1, whereby global U1, I mean psi prime of x equals e to the I phi with phi a constant psi of x. And our purpose in adding in this extra term was to get rid of those scalar modes. But by adding this particular form, we've actually accomplished a lot more than that. We have effectively enlarged this symmetry. Now this combined Lagrangian is invariant under a local U1 transformation. The local U1 transformation effectively allows me to do a different phase rotation at every point in space. Psi prime of x is e to the I phi of x psi of x. So now phi of x is a field over space-time. And that radically changes the structure of the transformation because now two different points in space can transform differently, arbitrarily differently. You can decide how you want them to transform, and they can be as different from each other as you want. And that sort of gets folded into this notion of the covariant derivative, because if different points in space-time transform independently of each other, then the notion of a derivative gets kind of messed up. You can't really compare 2 points that are close to each other in space because they could be very different in functional form. So that's essentially what's happening when we extend from this partial derivative to the covariant derivative.
Matt,
Sorry, sharing.
Oh, yeah, it's already sharing?
Yeah, yeah, we keep it sharing. That is the easiest way.
Oh, okay, great. So what happens to my Lagrangian under now this local transformation? My gauge Lagrangian was psi bar I d slash minus m psi minus e psi bar gamma mu psi a mu. So now if I transform the Lagrangian this way, L prime is psi bar prime I d slash minus m psi prime minus e psi bar prime gamma mu psi prime a prime mu. For the moment, I haven't decided at all what I'm going to do with a mu. You can imagine that I'm not transforming a mu at all, but let's just leave this free for the moment. All I'm going to do is transform psi. Just like before, this psi prime is just e to the minus I phi of x on this side, e to the plus I phi of x on this side, and the same thing over here. And at first glance, it doesn't seem any different from what we did before with the global symmetry, of course, because in the interaction vertex, this e to the I phi just exactly cancels that e to the minus I phi, and nothing special happens because they just multiply through to each other. Over here, however, something non-trivial happens. For the mass term, these guys cancel just like in the interaction term, but the derivative, however, changes the calculation because the derivative, when this is a field over space-time, the derivative can act on the field as well as commuting past it to act on psi. So in addition to the piece where the derivative acts on psi and the phase just comes right through, I also have a new term. So I still have my original psi bar id slash minus m psi. I still get back the original vertex, psi bar gamma mu psi, a prime mu, but now I get something extra coming from the transformation of the free term. When the derivative acts on phi, I get an extra minus psi bar gamma mu psi d mu phi. And this is interesting, and it's no accident, right? This is precisely the conserved current J mu. This object is exactly of the form of a scalar polarized mode of the vector field. So this is exactly as if I've added a scalar polarized mode to the vector field itself. So this gives me back, let's say, let me just write it like this, e slash minus m psi minus e psi bar gamma mu psi, and now my shifted field is a prime mu plus 1 over e d mu phi. So what we've showed then is that we get back our original Lagrangian. It's basically this piece. If I didn't transform A, if I left A alone and I only did that shift, then this would be my original Lagrangian. And this is just a shift by a scalar polarized mode. And we showed last time that the coupling of this form, this extra term that you are adding here, is just a total derivative of the Lagrangian. Basically, I can take this derivative and pull it out past that conserved current since d mu j mu is 0. And this extra piece is unphysical. It's just an overall total derivative to the Lagrangian. So the local U1 symmetry is equivalent to a shift by a scalar polarized mode. Meaning that this is unphysical or unobservable. And that's a good thing. So we set out to solve the problem of these scalar polarizations for the vector field. In the process, we've done something quite interesting. We've effectively enlarged the gauge. We started off with a symmetry group only of global transformations. And by extending the Lagrangian to have this particular minimally coupled form, we've created a symmetry which is now a local U1 symmetry. If I want to make the Lagrangian completely invariant, not invariant up to a total derivative, then this tells me how I should transform A to compensate for that shift of gauge. So this tells me my A prime mu plus 1 over E d mu phi should be equal to my original A mu, which gives me the transformation law A prime mu equals A mu minus 1 over E d mu phi. Make sure I didn't fumble minus something. Yeah, I think that's correct. Okay, so this is what I mean when I say that we have now extended the symmetry. We've enlarged the symmetry transformations of the Lagrangian. The Lagrangian now sort of lives in a much larger space. It's a function not only of space-time, but it's a function of whatever your gauge condition is. These are all unphysical degrees of freedom. The solutions can look very different in different gauges, but the observables that they describe have to be the same. So essentially what this is doing is we've now combined the symmetry transformations of space-time with the symmetry transformations of the gauge sector. So I tried to illustrate this. This is what the picture looks like in my head. Let me imagine that I fix a particular gauge. Let me say I choose d mu a mu is 0, which is Lorentz gauge. In a particular gauge, I've got my full plane of space-time, 4-dimensional space-time. But I have the extra dimension as well of different gauges that I could choose. So just for the sake of illustration, let me imagine that this is a family of gauges, d mu a mu equals a constant, and that constant could be 0, 1, minus 1, whatever you like, just so that there's an extra axis to my my combined manifold. It's no longer just space-time. And even though the space-time behavior may be flat, we're not doing general relativity yet, the different gauge transformations of different points act a lot like a curved geometry, right? So the fact that a point here may have a different gauge transformation from the point there can be thought of as the gauge dimension being curved in some sense. So this is a geometric interpretation of what we've done here. We've added in the extra gauge dimension, and with that extra dimension, the overall manifold isn't flat anymore. There can be curvature in the gauge direction, even though the spatial directions or the space-time directions may be flat. So this whole thing can be thought of very intuitively in terms of differential geometry on a curved manifold. That gives a nice interpretation of what this covariant derivative is actually doing for us. Okay, so to summarize in words, basically what we have done is enlarge the symmetry group from global U1 to local U1. This effectively unites space-time plus gauge symmetry. And it can be thought of as a curved manifold. Thought of as curvature in the quote-unquote gauge direction. For the moment, this gauge direction is relatively simple. There's only one kind of gauge transformation that we can make, sort of. You can shift A by a scalar polarized mode, but there's no color degree of freedom yet, which we'll have in a little while. So it's not like you have 85 different types of gauge transformations you can make. There's really only one where you shift A by a scalar polarized mode. This, by the way, the combination of space-time and gauge symmetry is an essential feature of a massless vector boson. Essential for any massless vector boson. It's quite non-trivial to show, but Weinberg does a good job of it in his textbook. If you start with a massless vector boson, it is not invariant under Lorentz transformations. So a vector boson does not exist unless it is a gauge boson, because it cannot be squared with special relativity unless you get rid of those scalar polarized modes. So this is not just nice, this is mandatory for the photon to exist. So when we talk about a gauge theory, this is really what we need. This is the picture in my head, that now we're working on a much enlarged manifold where we've combined the space-time and gauge information into a single set of continuous symmetries. What that does for us is that now the covariant derivative this is effectively acting as a, let me call it parallel transport. Comparator. So I don't know how well my picture is going to come across, but what I have in mind is something like, I have some point in space-time, and at this point I have my field psi of x. Somewhere else in space-time I've got the point psi of x prime. These guys transform differently, so if I want to compare them, I can't just take the derivative, the partial derivative that takes the limit as x prime goes to x of psi of x prime minus psi of x divided by x prime minus x. This would be my ordinary partial derivative. If we're dealing with a curved manifold, like transporting vectors around a sphere, then the direction in a gauge sense here could have shifted
because of the different gauge transformations over there. So I don't know. Suppose that I make a gauge transformation where my gauge direction is, I don't want to say pointing in a given direction. Let's say I have d mu phi, d mu a nu is 0 over here. And maybe I have d mu a nu equals +1 over here, just for illustration's sake. The fact that the gauge direction can be different, that there can be some curvature in this non-space-time direction, means that this derivative is not well defined. It's not a good comparison. And the covariant derivative effectively subtracts off that difference. It's a lot like parallel transport around a sphere, where your vector going one way has to curve as you go around the equator. It doesn't stay pointing in the same direction. So there's a lot that one can say to make this differential geometry relation more concrete. Effectively, what you're doing is that your vector field A mu is a connection coefficient. I think it's called a metric connection. The old school name for this is a Christoffel symbol. But it exactly describes the fact that you may have curvature in the gauge direction as you take derivatives in the spatial direction. So how do I see what the covariant derivative is doing? The definition was the covariant derivative on my field psi of x was a regular partial derivative of psi plus 1 over e a mu of x psi of x. So I see this by asking, if I define this new derivative, how does that derivative change? If I have now derivative of psi at this point, and I compare it with the derivative of psi, I guess not at that point. What I want to do is I want to see how this thing changes under a gauge transformation. And I want to see that it transforms locally. So if I take this object, my d mu psi prime is then the regular derivative on the transformed field psi of x plus 1 over e a mu prime of x psi of x. So this transformation is, psi prime of x. So this is d mu plus 1 over e a prime mu of x acting on psi prime of x. And now I plug in what these things are. The 1 over e here, a mu of x. Oh, sorry. Sorry, I wrote the wrong expression here. I'm looking at the wrong line. Let me fix this. So the covariant derivative was d mu plus I e a mu. Sorry, so this is now d mu plus I e a mu prime of x psi prime of x. Now it should work out. I get d mu plus I e a mu of x. The transformation of a comes in with an extra minus I d mu phi of x. Yep. And then the transformation of psi is e to the I phi of x psi of x. And this extra term exactly compensates for the contribution that comes when this derivative acts on the scalar field up in that exponent. So this extra derivative gets canceled out. When I take this derivative, I get plus I d mu phi, which exactly cancels this one. And then so the only thing that's left is the part where the derivatives all act on psi, and this phase just harmlessly comes through. E to the I phi of x, d mu plus I e a mu psi, and this is just e to the I phi of x times the original covariant derivative d mu psi of x. And so you should compare this with the transformation of psi itself. Psi prime of x was e to the I phi of x psi of x. And what we see is that the covariant derivative now transforms in exactly the same way as the field itself. It's now a local transformation. And you see exactly that the extra piece that's been added to the covariant derivative is exactly the right thing that cancels the curvature, the changing of the gauge direction, if you like, from one point to another. So this is your parallel transport operator. This is the gauge covariant derivative that in a meaningful way allows you to compare how do I take a derivative in this direction at this point or at this point, even though the gauge structure may be different, and how do I compare derivatives in different directions? This is what's going to give us the field strength tensor. Okay, questions so far? Yes.
So you can transform the derivative and psi and a mu. Are these equivalent transformations or are they doing different things?
They're all equivalent transformations. So the sort of original transformation that defines everything is this one. Once you define what the covariant derivative is, the covariant derivative will automatically do this for you by construction. And the transformation of A that we wrote down a moment ago also follows automatically from this definition. So I would say it's one transformation. These are all just different components of what that looks like. Okay. So the last piece that we need to complete the QED Lagrangian is the free kinetic term. And that requires defining the field strength tensor. This is F mu nu, which is just a generalized version of the curl. So compare this to, for instance, your intro physics relation that says that the magnetic field is the curl of the vector potential. This curl is just an anti-symmetric combination of derivatives. EI is epsilon ijk partial j ak. This is exactly the same structure. It's, let's say, the derivative along x of the y component minus the derivative along y of the x component. That's the curl. This is just the 4D version of that. The field strength tensor has a very simple relation in terms of the covariant derivative, which is powerful. This is the curl generalized to accommodate different space-time directions. That generalized curl doesn't yet take into account anything about the curvature of the gauge directions. So it should be, in some sense, a curl including the gauge directions. And since we know that the essential building block of a derivative is the covariant derivative, it's natural to ask, can I rewrite F mu nu in terms of the covariant derivative? Because the covariant derivative is the right object that takes into account the curvature in the gauge directions. The field strength tensor F mu nu is anti-symmetric by construction. So if I need an anti-symmetric combination of covariant derivatives, there's basically only one thing I can calculate, which is the commutator. Commutator of the covariant derivative d mu d nu acting on something for concreteness, let's say the field psi of x. This is an anti-symmetric object under mu goes to nu, and it has local gauge properties. So if I open up the brackets and calculate this, this is partial mu plus IE a mu, commutator with partial nu plus IE a nu acting on something like psi of x. The commutator of the partial derivatives is just 0. Because as long as you have a smooth function, it doesn't matter what order you take the partial derivatives. When the commutator involves the partial derivative and the vector field, you get an extra term, which comes from product rule, where the derivative acts on A instead of passing through to act on psi. Yes, sir?
Shouldn't the field strength tensor be independent of the gauge?
It is not necessarily. So the question is the field strength tensor independent of gauge? Yes for the case of QED, no for the case of QCD, and we will see why. So for now, we're calculating this commutator. The first term just involving two partial derivatives is 0. The other terms, the cross terms, which involve partial derivative A and psi, pick up an extra term where the derivative acts on A. So I get plus IE d mu A nu times psi of x. The other term has d nu commutator with A mu, but in the opposite order. So that comes in with a minus sign. D nu A mu psi of x. And the last term is just minus E squared commutator of A mu with A nu times psi of x. And A mu is just a number. It's just a scalar quantity, if you like, one component at a time. So these two terms are 0. These two terms are non-zero, and they exactly reproduce what we started off with. So this combination is just the overall factor, i.e. partial mu A nu minus partial mu A mu psi of x, which is just i.e. F mu nu psi. So this is just equivalent to what we wrote down over there. But because this object has simple transformation properties in the gauge direction, this is a much better way of writing the same thing. So I can effectively define this as F mu nu defined to be minus I over E commutator of covariant derivatives.
Yes.
Okay, so for QED, this is a little bit of overkill, but for QCD, this is going to save us quite a lot of pain, because now we'll be able to define minimal coupling by the introduction of a covariant derivative, and then knowing the covariant derivative, we'll immediately be able to find the field strength tensor. When we go to QCD, the transformation laws of the gauge group are much more complicated, and this will immediately give us the corresponding transformation laws of F mu nu for whatever choice we make for the covariant derivatives. Okay, how am I doing on time so far?
You have still more than 25 minutes.
Okay, great. Okay. Maybe let me write down the Lagrangian one more time, and then we'll compare things before we shift over to actually discussing QCD.
I have a quick question as well.
Yes, sir.
I'm just trying to complete the analogy. I think of the regular covariant derivative as the generator of infinitesimal parallel transport. Spits out a vector that's like as close as parallel to the neighbor right before it.
Right.
So this gauge covariant derivative, is it generating an infinitesimal gauge transformation,
Yes.
or is it still parallel transport in space?
Yes, it's both of these things,
It'll
right? So
follow
you're
those
only
three.
taking the derivative in the space-like directions. You're not like taking a derivative in the gauge direction. But you're allowing for the fact that you can have different gauge transformations at different points, and the infinitesimal difference in gauge transformations is enough to capture that curvature.
Okay.
So it's really like that differential geometry picture of you're zooming into a small patch and comparing how differently does the gauge transformation here vary from the gauge transformation there. So I think it's both. Okay, so let me try to summarize what we've accomplished so far. The process for how we constructed QCD, constructing QED. QED and other gauge theories. So first step was starting with the free Lagrangian. We started off with L equals psi bar I d slash minus m psi. Second step is introduce a vector field by minimal coupling. We said we're going to add to this Lagrangian coupling of the form J dot A. And I guess in between this, before you know how to add this extra term, you need to know what is the conserved current. That by itself is non-trivial. Maybe I should have made it an extra step in between, right? This involves observing what global symmetries you have here. For those global symmetries, constructing the conserved current by looking at the variation of the Lagrangian. And once you know what J nu is, then you can add A nu to your Lagrangian in such a way that you eliminate the scalar polarization.
Quick question.
Yes, sir.
And by minimal coupling, you mean that we've defined the interaction term in Lagrangian by simply using only a conserved current?
That's right. By minimal coupling, I mean exactly this, using only a J dot A as your interaction vertex, where the J here is specifically the conserved current J that came from whatever global symmetries you started on. Okay, so once we've done this, this is now gauge invariant, right? This is now invariant under local transformations. This step, as we just saw, is equivalent to defining the covariant derivative. So equivalently, instead of saying I've added a term of this form, I could say I've defined this covariant derivative and I make the replacement d mu goes to big D mu. That's exactly the same as this. Once I've done this, I have a perfectly good gauge invariant theory, but A mu is not dynamic. There is no kinetic energy for this A mu, so you can't have any propagators for this Lagrangian. This would effectively describe, say, the interaction of a charged electric system with an external photon. If I have A mu external, then this provides the vertex that tells me how it interacts with electrons and positrons, but this does not include something like a propagator that allows two electrons to talk to each other. To have the propagator, you need the kinetic energy, and that's where we need the field strength tensor. So step 3 is construct the field strength tensor. F mu nu defined to be minus I over E commutator of covariant derivatives. And then once you have this, now you can add in the free kinetic term, or let's say the pure photon term. Which is minus 1/4 F mu nu, F mu nu. And yes, so as was pointed out, the F mu nu itself is gauge invariant for the case of QED. It doesn't have to be in general. So if for QED, F mu nu is gauge invariant, so obviously F squared is also gauge invariant. And then this gives you the complete Lagrangian. This gives Lagrangian equals psi bar I capital D slash minus M psi minus 1/4 F mu nu, F mu nu. Simple to write down, but there's an awful lot under the hood for where it comes from and why. And the only ingredient that you need, this is the part that's so profound. The only thing that you need to define QED entirely, all of Maxwell's equations, everything, is just this, or equivalently just this, or equivalently just this. U1 gauge symmetry. Once you tell me gauge theory of U1, then I immediately know that's this conserved current, that's this vertex, that's this covariant derivative, that's this Lagrangian. So there is a one-to-one mapping between your choice of the gauge group and all of the physics that comes from this. So this is the overall strategy, and this is what's still going to work for us when we construct QCD. The one change is that we're going to switch up this gauge group. We're going to introduce new quantum numbers called color. Doesn't really even matter how many there are, although for real QCD there are 3 of them. That larger gauge group is going to allow now for rotations, essentially, where you can scramble up which color you start off with and which color you end with in many different ways. And changing this gauge group propagates down and is going to ultimately give us uniquely the QCD Lagrangian for SU3 gauge symmetry. So as I sort of previewed yesterday, the essential difference when I changed the gauge group from being U1 to SU3 or SUN, it doesn't even really matter how many colors N you have. That essential difference is going from an abelian theory, a scalar theory, if you like, where there's no direction information to the gauge sector. So this is a, let me call it directionless gauge group. This is what I mean when I say that charge is a scalar. It doesn't have any direction associated with it, and because it doesn't have any direction, it doesn't matter what order you do gauge transformations in. It's exactly like the case of rotations in 3 or more dimensions. If I always transform around the same axis, always rotate around Z, you can do as many rotations as you want and the order doesn't change. It's perfectly abelian. It's only when you have multiple independent directions that don't play nicely with each other that you have real commutator algebra that knows about the algebra of rotations. So the change that's going to happen when we go to QCD is that we introduce the fact that there are multiple directions of gauge transformations that can all work independently of each other. And because there are multiple directions of the gauge transformations, it means that we've introduced a matrix degree of freedom, and these transformations don't commute with each other anymore. That non-commutative nature of the transformations is going to modify the conserved current a little bit. It's going to modify the covariant derivative a little bit. It's going to modify the field strength tensor a lot. And that transformation of the field strength tensor is going to introduce essential new effects for QCD. This is the piece that's going to give us the gluon self-interactions, which is the entire story for QCD. If all QCD was is take this vertex and put a color factor on it, QCD would be really boring. The essential part of QCD is the gluon self-interactions, which come entirely from that gauge piece. So that's where we're going to go next. Do I have enough time that I should start the construction of QCD now? Or should we take some questions instead?
I mean, if there are questions.
How much time do I have?
More than 15 minutes.
More than 15 minutes. So,
17.
okay.
I would take maybe questions.
Okay.
And then we'll go from there. We can also split the 2 hours differently if you want.
Okay.
Yes.
We have the whole morning essentially.
Great. So yeah, why don't I pause here and ask if there's any questions or discussion that we want to have before we start repeating this process for QCD. Yes, sir.
Could you touch briefly on how this relates to the SU2 structure of the electroweak theory?
No, you just.
It's feedback, sorry. Yeah, absolutely. So we'll talk about that in detail in a few minutes, but very little changes if I work with a gauge group SU2 instead of SU3. The essential feature that gives us gluon self-interactions and all of this stuff is the fact that you have a matrix structure, SU something. Whether it's SU2 or SU3 only makes a tiny, tiny difference. And in fact, it's often advantageous to work in a general group SUN, and maybe even to consider certain simplifying limits of N. The thing that's maybe a bit different about the electroweak interaction is the fact that it breaks chiral symmetry, that it only couples to left-handed particles. So there's gamma 5s running around through the interaction vertex. It's not just J mu, it's more like J mu 5 or J mu minus J mu 5 so that you select only on the left-handed things. So as far as the gauge structure, I think it's extremely similar to QCD. You have the same kind of boson self-interactions in the electroweak theory, but it couples differently to the fermions because of the chiral symmetry. Yes.
Can I ask you?
Sure.
Okay, so the first one is, so there's one choice that you can make for the gauge frequency QED, is that right?
I said that, but it's a little bit misleading. I wanted to illustrate the fact that there's not multiple independent types of gauge transformations that you can make in the sense of many different generators of the gauge transformations. There's only one generator of the gauge transformation if you want. So all the gauge transformations are of this form, but your phi of x can be anything you want. So it's misleading for me to say there's only one kind because your phi of x could be as simple or as complicated as you choose it to be. But it's always of this form. And I'm comparing that, we'll show this again in a minute, for the case if phi was a vector, let's call it in some space. So we're familiar with this for the case of the rotation generators, where you have the angular momentum operators up here, and you have a series of rotation angles. There could be many phis. What I mean here is that there is only one phi. Phi could be a field over x, but there's only one of them. Here I can have many phis, and that's a much larger symmetry group because now I can rotate among the different components of these vectors. That's what I mean. Sure. And the second one?
So I don't know, maybe it's a perhaps without this question, but what would it look like to add a photon self-interaction? Do you have to like do another gauge transformation or like?
You mean in QED, literally a photon?
Yeah, photon interaction.
You cannot add a photon self-interaction to QED without breaking gauging variance. That's exactly the statement that was asked before about FU being gauging variance. So the self-interactions, as we'll see for gluons, come in here. It looks like not just d nu a nu minus d nu a nu, but you also get something which is plus g f a b c a mu b a mu c, where now these guys have extra color in this. So there is an interaction that gets created, which is in fact demanded by gauging variance if you have a non-abelian theory. This FABC comes from the commutator of the matrices. So if I choose a non-abelian theory, then the commutators of the matrices must appear here, and they must add a boson self-interaction to the theory. Conversely, if I have an abelian theory, this thing is strictly gauge invariant by itself, and I cannot add something like this without breaking the U1 gauge invariance. So I would say, no, you cannot have a photon self-interaction in QED, period, because of the U1 gauge symmetry of QED. If you pick a more complicated gauge group, we'll talk about this as well, you could, for QCD, right, QCD is the gauge group SU3. SU3 contains the 8 gluons, which are all charged. A very, very closely related group is U3, which doesn't have that special constraint. This has 9 gluons, if you like. It contains the same 8 that you had before, plus something proportional to the identity matrix. That identity matrix is a vector boson, which is neutral. It carries no charge of itself, so you might call it a photon. So there is a natural way to include something that looks like a photon in a theory that has boson self-interactions, but it's still the identity matrix. This is still the abelian subgroup. So this would still be a non-interacting photon piece of a U1, a U3 gauge theory. So maybe that's more information than you're asking for. I think the answer is in QED, no, you can't have a self-interaction. Photons in non-abelian theories are possible. Any other questions at this point? Cool. By the way, the procedure that I just wrote on the board, in my mind, this is the general procedure of particle physics. You can use this to invent any gauge theory that you want. Basically, all you have to do is make an experimental observation or make a guess. So you observe, hey, I watched an up quark transform to a down quark. How do I make a gauge theory that does that? Well, I put the up quark and the down quark in a matrix, and I ask, what kind of rotation could I have that transforms these guys among each other? If I observe experimentally that some process transformed up into down quarks, then I invent the matrix that does it. I take a wild guess at the group. I might pick, for instance, SU2 if I see a rotation among the 2 flavors of quarks here. And then I would take it and run with it. I would construct the Lagrangian of a gauged SU2 interaction. And this is essentially how you would end up with the electroweak force. Modulo this question about chiral symmetry breaking, where it's really only the left-handed pieces of the fields. There you have to work a little bit harder. So this is your general prescription for particle physics. Take particles that interact with each other, stuff them into a matrix, take your best guess at what kind of group might relate them to each other, calculate, and then compare with data. So you would do the same process if you want to construct your favorite grand unified theory. Yes, sir.
So the bosons are the mediators of the force between the
Yes.
particles, right? Now you said U3 has photons as well as gluons.
Yes.
So
1 photon, yes.
So does the photon also act as a mediator?
Yes, absolutely. So
all 9 of those bosons are the force carriers, if you like, of U3 gauge symmetry. The photon is only different from the gluons in that case because the photon is proportional to the identity matrix, so it commutes with everything. It's the abelian subgroup of U3. Okay, so now let's dive on into QCD.
Matt,
Yes.
Can we suggest us to take the break now and start?
Yes, I would like that very much.
Okay, okay.
Okay, let's take a bathroom break for a few minutes and then we'll start diving into QCD.
Yeah, we have
It seems like a natural pause.
15 minutes there.
Great.
So Okay, it works. Matt, they are all yours.
Okay. Okay, so let's carry on then. Now we're ready to apply this procedure to QCD and construct it. All right, so if I work on this procedure, the starting point for QCD is the free multi-component Dirac theory. So this looks very much like the starting point that we had before for QED. My free Lagrangian is psi bar I d slash minus m psi. The only difference here is that now I've treated psi and psi bar as if they are matrices. So this is a row matrix. My derivative operator here is not a matrix. It's just, if you like, proportional to the identity matrix. And then it multiplies a column matrix where the dimension of the matrix is totally up to me. I can choose how many components I want my fields to have. So for QCD, I want to define these fields to have exactly 3 components. So I will be 1, 2, or 3, which are often referred to as red, blue, and green, which is why we call it color charge. But it doesn't really matter that much how many colors you choose. As we'll talk about in a few minutes, it's often convenient to allow this to go up to some arbitrary number n, and c being the number of colors that you pick. So the essential change now is this addition of a multi-component theory. So just for absolute concreteness, this would be something like psi bar red, psi bar blue, psi bar green, ID slash minus m, psi red, psi blue, psi green. And so what this is going to do for us is it effectively enlarges our gauge group quite a lot. We do still have U1 symmetry. So I could, for instance, just make a rotation among psi and psi bar that redefines the real and imaginary part. I could do it just for the red quarks, or I could do it equally for everybody. That's going to give me back QED, exactly the same theory before, because it doesn't engage with that matrix structure in any non-trivial way. The interesting part is that now I have the ability to perform rotations among the matrix components. Still there. What's new is matrix degrees of freedom allow rotations among the color states, among the components of psi. So let me just start with a comparison to the rotation operator. The unitary rotation operator right? If I have in quantum mechanics, I have some vector v, then the transformed vector v prime is obtained by the unitary rotation operator acting on that vector. The unitary rotation operator is e to the I phi dot j, where j are the angular momentum generators. So that's jx I hat plus jy, j hat plus jz, k hat. And we know very well what those generators are. You can write them as derivatives for orbital angular momentum. If they're spin angular momentum, then they might be matrices, which is going to bring us back to SU2 in a couple of minutes. But the non-trivial structure is always of this form. I have e to the I phi, but now I have many components of phi. I have one phi for each generator. So now there are many fields phi which perform the transformation. So just as my J is a vector with multiple components, the transformation itself, the rotation angles, if you like, are also a vector. So I have phi for the rotation about x, I hat plus phi for the rotation about y, j hat plus phi for the rotation about z, k hat. So there is one type of gauge transformation, one type of gauge field, or one type of transformation, let's say, for each of the generators, for each direction or axis of your space. So this is what I mean when I say that your color charge or the gauge transformation is now a vector. There is one field phi, or one type of gauge transformation for each generator, meaning one for each axis of rotation. And in this example, since you're working in three-dimensional space, you have 3 generators for the 3 axes of three-dimensional space, and that's why you have 3 different components of the gauge transformation. What we're going to set up for QCD is essentially an 8-dimensional vector for the gluons that tell you all the different generators. Okay, so we'll go there now. Yes, sir.
So you said I can take any value up to NC.
Yes.
It would still be an SU3 gauge.
If you extend it to NC, it's the SUNC gauge group. QCD is the specific case, NC equals 3. Other questions? Yes, sir.
Shouldn't we be able to define this three-dimensional vector space using only 2 rotation axes? Or only 2?
Interesting. Why do you say this?
I'm thinking similar to the three-dimensional space analogy. I can produce arbitrary rotate. I can rotate my vector to any arbitrary direction in free space using only 2 rotations rather than the full 3 that you could use that are on the three-dimensional basis that you're on. But you could cleverly choose 2 rotations.
But which 2 rotations you pick are dependent on where you want to go, I think. It sounds like you're talking about Euler angles and how many Euler angles you need to specify the rotation. You still need all 3 generators to make all types of rotations. I think if you want a particular, I don't know, maybe I'm not saying it correctly. You definitely need all 3 generators if you want to be able to produce all 3 rotations in space.
I guess I'm wondering if there's some basis that looks more like a 2-dimensional basis in this space because we can reduce that degree of freedom.
Let me come back to that in a few minutes when I do the comparison to SU2. There is an important distinction between the, let's say, 2x2 matrices of the Pauli matrices, which do rotations of spin, but the fact that there are 3 of them, which is the 3 axes of space. What now I'm talking about is the number of generators, which is related to the number of axes or the dimensionality of the gauge group. And that's different from the dimensionality of each matrix itself or the generator itself. So I don't know if that's going to answer your question, but feel free to ask it again after I discuss that. Okay. Other questions at this point? Okay. So we've established that the kind of transformations that we're interested in constructing a gauge theory for are these rotations. By the way, how do we know that the number is 3? The number of colors is 3. Anybody know? Experiment. I'm thinking of a particular particle that's observed that without having 3 colors couldn't exist.
Proton.
Proton's important, but the proton doesn't have to have 3 colors necessarily. It's a baryon. If you had a baryon with all 3 quarks the same flavor. Yes?
Delta plus plus.
Delta plus plus? What's the core content of delta plus plus? Up. That would do it. I'm not sure about the spin configuration of the delta. Maybe that's also going to work. The one that I have in mind is the omega minus. The omega minus is made of 3 strange quarks. The omega minus is a spin 3/2 particle. So your quark model picture of this thing would be that all 3 quarks have the same spin, all 3 quarks have the same flavor, and this was a significant reason why people didn't believe quarks were real when Gelman first proposed the quark model. They said, obviously, this violates the Pauli exclusion principle. So you can't have this. Quarks might be a nice organizing scheme, but they're not real, especially because nobody could find one looking for quarks in their detectors. And so QCD solved this because if I have 3 colors, I could have color I equals red, blue, or green. This introduces exactly 3 new dimensions that allow me to anti-symmetrize this under color space, even though flavor and spin and everything else could be totally symmetric. So you do need input from experiment to help tell you that the number of colors is 3. Yes, sir.
But this case on the test, there are at least 3 curves, but there can be 4 or 5 on this group.
It needs to be color neutral with the sum of them. I'm not sure I could do that with SU4. If I added up 3 of them and there was some overall color left over, then this thing would be strongly interacting, just as strongly interacting as a single quark would be. So I think that object would still be confined and you wouldn't be able to see a 3 quark baryon being made out of an SU4 group. So I think it does need to be 3. So, okay, just a side comment about where that number 3 comes from. Okay, so the kind of transformations that we're interested in are free Lagrangian. We have psi bar I, ID slash minus M psi I. This is often written psi bar ID slash minus M psi, exactly as we had before, with it just being implicit that you have to remember that now these are matrices. So keep in mind what's being shown and what's not being shown. The transformation that we're interested in is the rotation matrix psi prime equals a unitary rotation of my original psi. So in a component form, this would be psi prime I of x equals unitary operator ij acting on psi j of x. So this explicitly allows a rotation or a mixing of the matrix components. The type of rotation that I want to make here is something of the form exactly as we saw for the rotation generators. It should be e to the I phi dot, let me call them t, psi j of x. And then written in terms of components, this is e to the I phi a t a ij component, psi j of x. So here I've written phi as a vector. So this is, I don't know how useful this is, but you can think of it as a vector with unit vectors pointing in your gauge space. The generators T are what define the algebra of the group. So these are just unit vectors. And these are the important things. These are the generators of SU3 or SUN. So this is the generalization of the rotations that we saw. The rotation group in 3 dimensions is, of course, SO3. So that was why we ended up with 3 directions. For a different gauge group, I could have different number of generators. I haven't figured out yet what those generators are. But however many of them I have to sum over an independent phi for each one. So, okay, now let's talk about the structure of the group. The gauge group that we're working with is SU3. What does SU3 mean? S stands for special, U stands for unitary, and 3 is, of course, 3 by 3 matrices. So unitary, we know what that is. U dagger is U inverse. 3 by 3 matrices, that's because you have red, blue, and green that you could rotate between. And special is an additional constraint which requires that the determinant of the transformation be 1, not -1 or something else like a complex phase. In terms of the rotation group, this means that you have pure rotations and no reflections, that the complete group also includes discrete reflections as well. Determinant equal to 1 basically singles out just the continuous subgroup of that. In terms of the transformations, determinant of this unitary matrix being 1 is equivalent to the trace of the generators being 0. So this implies trace of TA is equal to 0. And as we've already mentioned a little bit, this constraint basically forbids the unitary transformation being proportional to the identity matrix, 1, 1, 1. This is obviously the generators being proportional to you, sorry. So if I had a generator that was abelian, something that was proportional to the identity matrix, then that would be like a photon. That would be the abelian subgroup. And the special constraint basically says you don't have a photon in this theory. If you wanted a photon in the theory, then you should, instead of SU3, have been working with U3. Okay, so that is the definition of the group.
Do you still have conserved currents if you lift the special requirement? If you
Yes,
don't-
in fact, you have one more conserved current, which is just the original electromagnetic current, psi bar gamma mu psi.
Even though that reflection is not a continuous symmetry, it's a.
Yes, that's exactly right. So the SU basically gets rid of the discrete subgroup and leaves you only with the continuously grouped part. If you kept it around, you would basically have two separate groups. You'd have the U1 and you'd have the SU3, and they wouldn't talk to each other.
Thank you.
Okay. So now I have to be more specific. What are the generators of SU3? So what are these TAs? We write them as 1/2 of just conventionally the Gelman matrices. So these lambda A's are referred to as the Gelman matrices. How many of them are there? There are 8. A equals 1, 2, up to 8. Where does that come from? That basically comes from all of the independent degrees of freedom in the gauge group. That I have 8 independent choices that I could make. And that the reason that I have 8 is basically because I have 3 by 3 matrices. So I could have 3 choices for the initial color, 3 choices for the final color. That would be 3 squared. So you would think there should be 9 gluons. That's the usual fairy tale story that we tell in colloquia, where you say, oh, for every color you have initially, you have every color finally, and that's where the gluons come from, the limitations among the colors. That would give you 9 of them. The special constraint, which throws out the diagonal photon piece, subtracts 1. So this is where the 8 comes from. In general, the SUN gauge group, SUNC, your A could go from 1 up to NC squared minus 1. So here are the 8 Gelman matrices. The factor of 1/2 is totally convention. Some people choose a different convention, but this one is fairly standard. It's also highly analogous to the Pauli matrices. So what are these things? There are 8 of the matrices, and they fall into a very familiar structure. So lambda 1 is this off diagonal 1, 1. Lambda 2 is this off diagonal I minus I. Lambda 3 is this on diagonal 1 minus 1. And if I scratch my head and stare at that for a second, I know exactly what those matrices are. What are they? The Pauli matrices. The Gelman matrices are nothing but a generalization of the Pauli matrices. Lambda 1, 2, and 3 are just sigma 1, 2, and 3 sitting up in the top left corner. You also have analogous quantities. Lambda 4 is like sigma 1, sigma x, but now between the other 2 color combinations. So this is like a sigma x rotation among red and blue, if you like. This would be like a sigma x rotation along red and green. So I have similar combinations for all of these things, something like this for the others. And then you have a couple of extra pieces that don't look exactly like the 2 Pauli matrices. So I've got one set of Pauli matrices, that's 3, another set of Pauli matrices, that's 6, and then 2 other generators down here. This lambda 8 is diagonal, but still traceless. This is not the photon. Okay, so just for specificity, those are what the Gelman matrices are. Very rarely do you actually have to plug in the specific form of the Gelman matrices, which is part of why it's convenient to shortcut from SU3 to the more general SUN. The thing which defines the group in all of its representations, not just the 3 by 3 defining representation, but in all of those representations, is the algebra of the group. The thing that makes it SU3 is the commutator algebra of TA with TD. And this is I, F, ABC, TC. So Lie groups, these continuous symmetry transformations, always have a transformation of this form. The thing that you have to specify that uniquely identifies what group you have is what are those structure constants? Which particular values do you have? So if I'm telling you the specific Gelman matrices, the next thing I have to tell you is what specific structure constants. Here they are. So the definition is from the commutator algebra. Basically, it's like saying that your TAs, these generators, are a complete basis for the vector space. So whatever this commutator is, I have to be able to expand it in a basis of the generators themselves with some coefficients. And these are those coefficients. Only some of them are non-zero. So this is a table I made. You have f, a, b, c for different possible values of a, b, and c. So if I have f 1, 2, 3, the value is 1. If I have f 1, 4, 7, I get a half, and so on. These are the only non-zero values of the structure constants. The structure constants, by definition, are anti-symmetric. They are totally anti-symmetric under this exchange of any two indices. So it's obvious from this that A and B on the left are anti-symmetric because they're in a commutator. So that tells you already that FABC is minus FBAC. Maybe a little bit obvious that the antisymmetry also extends to the index C, but it does. So if I swap A and B, I get a minus sign. If I swap B and C, I get a minus sign. This is awfully familiar. This sounds very much like the antisymmetric Levi-Civita symbol. Epsilon ijk, which also has that totally anti-symmetric property. For very good reason, the epsilon ijk are the structure constants of SU2, which we'll talk about in a moment. Question?
Yeah, you said that some values of the FABC are 0?
Yeah, so the ones that I've shown here are the only non-zero ones. So by definition, if I have any two indices that are repeated, it's all automatically 0. So if I had F 1, 1, 2, that's guaranteed to be 0. If I had, I don't know, F 1, 2, 5, that's not on my list here. If it's not on my list here, it's 0. So these are the list of the non-zero structure constants. Everything else is 0.
What does that imply in terms of like actual work? Sorry, that's a good question.
Let me give an example in a moment and then tell me if that answers your question or if you're still confused on that. Okay, so these are the structure constants. Again, rarely do you actually have to plug in specific numbers for these things. Much more often you're using identities similar to the identities for the Levi-Civita symbol when you sum over repeated indices. Okay. We've had very good questions so far about the comparison to SU2. Before I make that comparison, there's one other thing that I need to mention about the structure of this group. So the 3x3 matrix representation of SU3 is the fundamental or defining representation. And this one corresponds to the quarks. So when I set NC, NC is the number of colors of the quarks, and anything which is described by those 3x3 rotation matrices is basically always a quark. The fact that it's 3x3 means it's quarks. There is another representation of SU3, which we've already got all of the information needed to construct, which describes the gluons. This is called the adjoint representation. There is also an 8x8 representation called the adjoint representation. Which describes the gluons. And this is constructed from the structure constants themselves. So it requires a little bit of algebra that I'm not going to go through here. But I can define a different set of generators, let me call them capital TA with indices BC, that are defined to be negative I, F, ABC. So this object is an 8x8 matrix, BC. So this is 8x8, and there are 8 of them. If I use the structure constants to define these new generators, these generators satisfy exactly the same algebra as these ones do. So if I take those capital T's and I plug them in here and I calculate their commutator, that commutator is exactly I FABC, capital TC, the same FABC. And because the algebra of that representation is the same, those are the same group. They just look different. This is the 3x3 version of the group. This is the 8x8 version of the group. But the algebraic properties are totally identical. The ingredient necessary to prove this is the Jacobi identity. This is just a general property of commutators. For us, we need it in the form commutator of TA with TA with TB and TC plus all cyclic permutations. So then I do TB commutator with TC TA. And then I do commutator of TC with TA TB. And the sum of all of those things is 0. Basically, if the commutators are totally anti-symmetric, so if I add up all cyclic permutations, it has to add up to be 0. Sorry, it's squeezed down here at the bottom. It's also in the lecture notes, so you can go find that if you can't see it here. Okay, so this is important. 2 different representations. There's actually a lot of representations of SU3, but these are the most important ones. These are the representations that correspond to quarks and gluons. Okay, now let's try and unpack the structure of this group a little bit more. How am I doing on time?
Okay.
Whatever.
Alex had to step out for a second.
Oh, okay.
So I don't know. Just go.
Carte blanche. Got it. Oh, questions? Yes, sir.
Other representations.
Yes. Sure. The easiest way to do it is just by taking superpositions of lower dimensional representations. So you can think of your proton, for instance. This will maybe illustrate what I'm trying to say, but it doesn't show you one of those higher dimensional representations. So you could have, for instance, the proton where each quark is a triplet representation. So this is a fundamental, this is a fundamental, this is a fundamental. If I add 2 quarks together, 3 plus 3, the 2 quarks could add up to give me, let's see, 3 times 3, I should get 9 of them. So I'm going to get a 3 bar representation plus, and my group theory is rusty. It looks like it's going to be something fine. Okay, I don't know, I'm screwing this up. The point of this is you can add up the representations of 2 quarks, and it looks as if you have 1 quark and something with an anti-quark representation. It looks like the 3 bar representation. So it looks in terms of color as if you added up 2 quarks and you got an anti-quark. This is what goes by the name of a diquark in the literature. It's specifically 2 quarks that combined together are in an anti-triplet representation such that it sort of looks like a meson between a quark and an anti-quark. In the same way, if I have a quark and a gluon, I can have an octet and a triplet, and then I could combine them together and I would get all possible representations. So if you have the defining representation, then you can basically construct higher representations by direct products of lower dimensional representations.
Then 3 and 8 are the lowest dimensions.
Yeah, 3 is the lowest dimension. That's the defining representation. There can't be anything lower than that. Once you have the fundamental, you automatically get the adjoint for free from the structure constants, and then everything else is higher dimensional. Okay, so we've already talked a bit about the analogy to SU2. It's really more than an analogy. So for SU2, as we've seen, the unitary rotations are just e to the I phi dot sigma, where sigma are just the Pauli matrices. So this is e to the I phi a sigma a, where a equals 1, 2, and 3, and these are just the Pauli matrices. The Pauli matrices, of course, are sigma x 0, 1, 1, 0, sigma y 0 minus I 0, and sigma z 1, 0, 0, minus 1. And so this is the part where it's very helpful to have SU2 to benchmark. The Pauli matrices are 2x2 matrices. And that's because the quantum number that they describe rotations of comes in only two types. Right, so this acts on a quantum number with two states. Normally, we talk about them as rotations between spin up and spin down in a rotational symmetry context. You could have equally called those colors, or you could have called them isospin, or you could have called them whatever you want. This is just a quantum number that comes in exactly two outputs. So the matrices themselves are 2x2, telling you about the dimension of that quantum number in the fundamental representation, but yet there are three Pauli matrices. So there is a significant difference between the dimension of the fundamental representation, which is 2, and the dimension of the adjoint representation, which is 3. So in this case, there are, let's say, NC equals 2 varieties of the quantum number. And so this means that they are 2x2 matrices in the fundamental representation. But there are NC squared minus 1, that's 2 squared minus 1, which is 3 different Pauli matrices. And that reflects the axes of rotation. So the reason there are 3 Pauli matrices is because there are 3 independent axes of rotation that you could choose to transform between the two spins. It sounds a little counterintuitive. I only have 2 spins, but yet I've got 3 different ways to rotate between them. That disparity is only going to increase when I have 3x3 matrices, but 8 ways to rotate between them. But this is perfectly familiar to you. So with this in mind, I will interpret the rotations TA in QCD as the axes of rotation, axes of color rotation. So QCD then has 3 different color states for the quarks, but 8 possible ways to rotate among them, because now I have many pairs that I could choose. So just for a concrete example then, if I perform a particular rotation, let's say I want to rotate between red and blue, which for the sake of specificity, let me call red I equals 1 and blue J equals 2, using a particular axis. How about A equals 1? So if I pick those things out, I'm talking about a particular Gelman matrix. I'm talking specifically about lambda 1 if I pick A equal to 1. So this particular example would mean I start off with, let's say, psi red 0, 0. I'm going to hit it with lambda 1, which is 0, 1, 0, 1, 0, 0, 0, 0, 0. And I'm going to project it onto blue. So 0, psi blue, 0. So picking out red here and picking out blue here is effectively picking out this particular element of the matrix. This particular element of the matrix lambda 1 is what describes that unique rotation. So this is what I had in mind for an answer to your question, ma'am, about plugging in a specific rotation and what that might look like. If you wanted to perform a particular rotation between specific colors along a specific axis, I think that's what it would look like. You could plug this into the exponential of the matrix. So just for specificity, I think this is what it means. You would pick out which colors are involved in the rotation, which axis you're performing the rotation with, and that will uniquely define what transformation you're doing. Okay, oh yes, and of course, the Pauli matrices themselves come from SU2, and SU2 exactly satisfies this relation. The TA with the TB is I, F, A, B, C, T, C, where now A can just go from 1 to 3, and the F, A, B, Cs are just the Levi-Civita symbol, epsilon at A, B, C. So you start off with learning about the epsilon symbol, but this is really just your first introduction to structure constants, and very little changes if you go between these epsilons and a more general FABC for QCD. So this was the comparison that I wanted to make before I move on to large NC. Are there any other questions at this point? Yes, ma'am.
So still about FABC being 0. So I mean, that would mean that it not being 0 is what makes this not abelian, right? So like if you had an FABC that was 0, would that mean that, like, you know, rotating between blue and blue is meaningless?
I think it means that a certain generator cannot perform that rotation. So if I pick this A equals 1, this matrix only has non-zero elements in the red-blue sector. So this axis does not rotate involving green. So you have to pick a particular rotation to perform the rotation that you want between the specific colors. Does that help? Okay. Other questions at this point? Okay. So we've been talking about SUN for n different than 3. Very little changes if you allow n to be generalized away from 3. And in fact, you can get quite a lot of advantage if you keep n flexible and take certain limits with it. In particular, the limit of large NC is especially powerful. This, by the way, is attributed to Gerard 't Hooft, the 't Hooft large NC limit. Formally, what we mean is we're doing still a calculation at weak coupling. So it's sort of a modification or a resummation of the perturbation series. So you're still working at weak coupling, where alpha is much less than 1, but I want to consider the limit when my gauge group is SUNC and NC is going to infinity. Of course, I can take these limits in different ways, so I have to specify how big or small these two numbers are relative to each other. The 't Hooft large NC limit is the limit when the product is a constant, and I think technically that constant is assumed to be small. This combination, I believe, is referred to sometimes as the 't Hooft coupling. Why is that helpful? For one thing, the large NC limit greatly simplifies the theory because it's dominated by gluons, just because there's more of them. The number of quark colors is NC. The number of gluon colors in the adjoint representation is NC squared minus 1. So just on simple counting alone, if NC is going to infinity, you can totally forget about quarks in your theory. So the large NC limit of QCD is a gluon-dominated limit. Large NC equals only gluons, unless, of course, you calculate corrections beyond the NC going to infinity. But these would be corrections suppressed at large NC. So first benefit that you get is forget about quarks. That helps. Second thing that you benefit from is the -1 now becomes totally unimportant. And you can just call this NC squared. And that -1 came from requiring that I don't have a diagonal part of this gauge group, getting rid of the photon piece, if you will. So the large NC limit basically says you can keep or drop the photon and nobody cares. So you can think of this as generalizing the group back from SUNC to UNC. And that actually simplifies some of your color algebra quite a bit. Let's see if I can put some space down here. SUNC goes to UNC. And this is also a good thing. Why is it a good thing? How do I see that it's a good thing? One way to see it is through the Sievert identity, which is, again, extremely useful. This is just a general algebraic property of the gauge group. So whatever representation you have, if I combine two generators, TA, TA repeated, with arbitrary other indices, ij, kl, they can be doing whatever they want in the rest of the diagram. You can think of this like a gluon propagator, at least just the color space part of it. So this is something like, I have a color, a fundamental color, which comes out I and came in J. I have another fundamental color. Yes. That goes out K and comes in L. The Fierce identity is this combination just from repeating these indices. It's just a certain combination of Kronecker deltas. So it's 1/2 delta IL, delta KJ. So it sort of picks out this I with that L and that K with that J, a non-trivial cross between them, minus 1/2NC delta IJ, delta KL. So this is just similar to the identity for repeated indices of the epsilon tensor. Visually, you can think of this as the color flow being carried by that octet representation gluon, the adjoint representation gluon, is half of just pairing up the fundamental colors in a certain way. This delta function tells me that I equals that L. So it looks like that color went straight through from L to I. This one tells me that my J is now the same as the K. It looks exactly like my gluon is just two quarks sitting on top of each other. And this quark carries the color flow this way from J to K. This one carries it this way from the L to I. And then the reversed term is minus 1/2NC. And the Kronecker deltas now basically pair things up like this. So now I have I, J are equal to each other, and L and K are equal to each other. This identity is true in general for finite NC. This is a super helpful algebraic property that can help you evaluate traces of color matrices in the diagrams. What does large NC do for us? Large NC gets rid of the last term. This 1/NC term is exactly the term that enforces the special condition. This is the one that requires that if I contract I with J, I should get 0, because that's the trace of TA. If I'm working in SUN, then that should be 0, and this is the term that guarantees that it's 0. At large NC, who cares? I don't need to make this thing 0 anymore. I throw this away, and that means my flow of color is actually extremely simple. And so in a remarkable way, at large NC, you can take a gluon, at least in terms of its color flow, and replace it by two quarks in the fundamental representation. So this octet color flow of gluons becomes exactly 3 plus 3 bar, or 3 times 3 bar. So large NC helps you, it gets rid of the quarks and you have only gluons. It simplifies the theory. That makes your color algebra very simple. And one nice consequence of that is that you get only planar diagrams. So in terms of a graph theory perspective, so something like if I have two particles up here and something down here, and they interact with gluons. In this large NC limit, that gluon can be replaced by a double line, exactly as if a quark coming in exchanges a quark and an anti-quark. Planar refers to the statement that the lines don't cross underneath each other in a graph theory sense, that you could lay it all out and every vertex could lie in a plane, and you don't have something like this where a gluon would need to cross underneath it. That would be a non-planar diagram, and you can show that if you have something like that, it's suppressed by a power of NC. So large NC limit is super duper helpful, but it's only super duper helpful for observables that are dominated by gluons. Large NC is a great approximation for gluonic observables. And this will be a saving grace for us when we try to construct and solve the small x evolution equations, because that phenomenon is gluon dominant. The general problem, including finite NC, is an infinite tower of differential equations that you have no hope of solving. But in the large NC limit, where the quarks go away, the color algebra simplifies, you get one differential equation in closed form that you can solve. This was the large NC limit. Oh yeah, corrections to the large NC limit. That was the last thing that I wanted to say. How good is this as an approximation? Real QCD is not NC going to infinity. Real QCD is NC equals 3. So if real QCD is SU3, not SU NC going to infinity, most observables that you calculate, at least all the ones I'm familiar with, typically have corrections that are of order 1 over NC squared. If you're thinking of it like an expansion of NC as NC goes to infinity, then you've got the 0th order term, that's the large NC limit, and then there are corrections to it. You could have a correction of order 1 over NC, but that's pretty unusual. Most of the time they come in as 1 over NC squared. So if I do a large NC approximation and then I try to use it for NC equals 3 in QCD, I expect that my error should be of order 1 over 9, which is about, let's call it 10%. So you would naively expect that the large NC limit should be accurate at a 10% level for an approximation to QCD. But in practice, for gluonic dominated observables, it actually works much better than that. In practice, it is often much better at, say, a 1% level. Than this naive estimate. That doesn't mean that you can do everything with it. You have to pay careful attention to which observables need the quarks there. So when you start doing polarized evolution at small x that has not just gluons but quarks in it, then large NC is not necessarily the best way forward. You might want to take some limit where NC gets large and the number of quarks gets large too. And that's a different story. Okay, but for our purposes, large NC will be extremely helpful in deriving and solving small x evolution equations. Questions at this point? Yes, ma'am.
Do we know why it tends to work at the 1% level?
I don't recall off the top of my head. I read a paper, I think Thomas Lappy was the author of this particular one, that showed how it worked out. I don't remember the details, but there are papers in the literature that examine specific observables and NC corrections to them, and that can answer for a specific case why it works better. I don't think it's guaranteed to always work better, but we just get lucky for certain things. Okay. If there are no other questions, then let's start gauging this thing. Now the path is clear. Time, order of magnitude.
It's 10 minutes.
That's actually not crazy. I might be able to do it. Okay.
We can have also 5 minutes more.
I think we're within error bars. Let's give it a shot. Okay, first thing that I need to do is I start off with my free Lagrangian. We already have this. So I have now writing this in abysmal matrix form, psi bar IV slash minus m psi. Where warning, these are now matrices that I now have to start paying attention to their computations with each other so that I don't have to keep writing I and j for everything. Second thing I need to know is what is the symmetry or what is the conserved current associated with the global symmetry? So my global symmetry is the SU-NC transformation. So my psi prime is e to the I ta phi a psi, where phi a are all constants. If I plug it into my Lagrangian, then I trivially again get L prime equals L is invariant. Exactly the same way as before. You get unitary operator here, opposite of the unitary operator there. If everything is a constant, this just slides right past the derivative and they cancel each other out. It's convenient, by the way, for me to refer to this sometimes as just the unitary matrix. So the Lagrangian is invariant. That means that delta L is equal to 0. And by chain rule, delta L is expressed in terms of derivatives with respect to all of the functions in the Lagrangian. So just like before, delta L is 0, and I can write that 0 as delta L with respect to psi times the variation in psi, delta L with respect to psi bar times the variation in psi bar, plus delta L with respect to the variation in the gradient d mu psi times the variation of d mu psi. Just like before, I use the equations of motion. The equations of motion tell me this thing equals 0 by the Dirac equation. So after I take this derivative, the rest of the thing is 0. This is not zero, but I can relate it by the equations of motion to d mu of variation of the Lagrangian with respect to the gradient d mu psi. Delta psi, and just like before, I can swap the order of these derivatives to write it as the gradient of the variation delta psi. And now with this term gone, this one and this one combine together in the form of product rule, and I get 0 equals the total divergence of variation of L with respect to the gradient d mu psi times delta psi itself. This is now the conserved current. So we get d mu j mu a equal to 0 with j mu a. If you actually calculate the derivatives and plug it in, you get psi bar gamma mu ta psi. So this is exactly analogous to the electric current that we got for QED. It's still the psi bar gamma psi in Dirac space, but now there's a color rotation involved. If I write this out in terms of the I and j components, this is psi bar I gamma mu psi j times ta ij. So it's still the same like particle minus antiparticle number current, but with different colors. There's a mixture between red and blue or blue and green, and you can have one current for each possible way of rotating between them. So there are now nc squared minus 1 equals 8 conserved currents. Did I see a question? Yes, ma'am.
Yeah, for the DL, I was wondering if this is QED too. The third term, why do we not have the equivalent term for psi bar?
Oh, because the Dirac Lagrangian is asymmetric, it depends on d psi, but not d psi bar. So here the d slash only acts on psi. There is no derivative acting on psi. Okay, so we found the conserved current. Now we know what term to add to the Lagrangian. Yes, sir.
So that generator, lowercase t a.
Yes.
There were 3 of those. So how do we get the 8 conserved currents?
No, there are
8.
the value of a in SU3 or in SUN can go from 1 to nc squared minus 1. So a here is 1 to 8, but the dimension of TA itself is 3 by 3. So the size are the 3 component matrices. This is a rotation among them, but there are 8 different choices of the rotation, one for each axis of rotation you could have. Okay, so now we know how to define the gauged Lagrangian. So the gauged Lagrangian is the one that I started off with, psi bar I d slash minus m psi, plus or minus whatever you pick, since it's all arbitrary, j dot a. So in this case, I'm going to call it plus g times this current, psi bar gamma mu ta psi times a mu a. And again, I have 8 currents, so I have 8 gluons. This is now, if you like, a vector product in 2 different ways. It's a vector product of the Lorentz vectors mu, and it's a vector product of the gauge vectors a. So G here is an arbitrary coupling constant. This is, for QED, this is what we call minus E, the charge of the electron. So now we're calling this plus G, that would be the color charge of a quark, I guess. It's the unit of color charge. In QED, we introduced this thing with a minus sign. Now I'm introducing with a plus sign. That's all pure convention. So pay careful attention which textbook is using which convention, because they don't all agree with each other. With this definition, I can again absorb the new term back into that partial derivative. So this is again gamma mu partial mu. So I can write that as psi bar I gamma mu, the original partial mu that I had, and if I have plus G, then I need minus G a mu a ta. I pulled out a minus, so it needs minus I. Minus m psi. Yes. And this is now my covariant derivative.
one of your ASPs?
No, good question. So the upper and lower indices is only important for the mu's and the nu's, for the Lorentz indices. That's because the metric tensor knows the difference between the space-like and the time-like. For SUN, for the gauge transformation, there's no difference. There's no special index that changes whether it's up or down. So there's no meaning to the placement of A, B, and C up or down. There's no meaning. You could ascribe a meaning to I and J being up or down, but generally it doesn't. So I would say the mu's and nu's being up or down is very important. The A's, B's, and I's and J's are not. Okay, so now that we have the covariant derivative, we can immediately use that to construct everything else. It's perfectly fine to just keep the covariant derivative and run with it, but it's useful to see what that implies for the explicit transformation law of A. We said the transformation of the covariant derivative is defined in such a way that d mu on the field psi after the transformation equals the unitary matrix acting on the covariant derivative itself, right? So psi transforms with the unitary matrix U. The covariant derivative cancels out any extra terms so that U basically slides right past. This is the definition of what the covariant derivative is supposed to do. And so if I plug this definition in, then I have d mu minus IG A mu A TA acting on psi prime equals U acting on d mu minus IG A mu A TA acting on psi, and psi prime is just U times psi. So you can rearrange this equation and solve for it. Basically, you multiply by U dagger on the left, you cancel the common terms, and you solve for, oh, I forgot this, this is important. This on the left is the transformed A. I'm using this to figure out what the transformation of A is. What I get from solving this expression is A mu A TA, that product, equals A mu A prime times the rotated color matrix U dagger TAU plus I over G U dagger derivative of U. Quite a complicated transformation, much more complicated than in QED. Here we've expressed it compactly in terms of the matrix product as a matrix multiplication. You could also do it component-wise. If you break it out in terms of components, then what you get is A mu A prime equals A mu A plus 1 over G d mu phi A plus F ABC A mu B phi C. And this is a different gauge transformation than what we had for QE. There's still the addition of a scalar mode. Still plus scalar polarization. But now also something else. This is a color rotation of the gluons. So the gauge transformation is more complicated. It involves still the scalar mode. It's still necessary to have this to get rid of the unphysical scalar degrees of freedom. But now you also have that matrix playing a non-trivial role here in the adjoint representation, rotating the colors of A. Okay, once we have the covariant derivative and we have the transformation of A, we can also now immediately get the field strength tensor. Okay, so the last thing that I need to do is I need to calculate the commutator of two of these covariant derivatives, d mu and d nu. And this is an operator acting on something like the field sum. So this is the commutator of d mu minus IG A mu A TA with d nu minus ig a nu b tb acting on psi. Here I've just chosen to call this a different index so that when I start expanding this thing out, I don't accidentally repeat A more than once. So again, when I open up the commutator brackets, the commutator of the partial derivatives is just 0. So I still get the same thing that I had before. I have cross terms where the derivative acts on the field. That's going to give me minus ig d nu a nu b tb for this term. This cross term comes in with a minus sign because the commutator is in the other order, plus ig d nu a mu a ta. But now I also get something non-trivial from the last term. I get minus g squared a nu a nu b, commutator of the color matrices. This first set of terms is exactly what we had before. This is the, if you like, abelian part of the field strength tensor. This part, however, is fundamentally non-abelian. This is bringing in the structure constants IF, ABC, TC. So what this gives me is minus IG, d mu, a nu, I'm going to rename the color index C so that I can combine like terms. So that's the first term, and I also have minus G squared, IG squared, a nu B, F, ABC, TC, acting on psi. And now I can pull out common factors. Everything has a minus IG, everything has a TC. And what's left is d mu a nu c minus d nu a mu c plus IG F ABC a nu b times psi of x. So this commutator of the covariant derivatives, we use this to define this as the field strength tensor. So this object then is the natural extension F mu nu C, if you like. Sometimes you see F mu nu C combined together with the generators themselves. So you'll see sometimes F mu nu equals F mu nu A TA. The important thing here is that the structure of the gauge transformation has changed the content of F mu nu. It's added in an extra term, which is very non-trivial. This one piece is the central culprit for all of the interesting physics of QCD. This is the gluon self-interaction. So once we have the field strength tensor, we can construct easily the pure glue term. So we said our gauged Lagrangian could be written psi bar I capital D slash minus M psi. And now we're going to add to it the pure glue term, which is minus 1/4 F mu nu A, F mu nu A. Important to note, this field strength tensor, F mu nu, has a color index on it. It is not gauge invariant. This object is explicitly an 8-dimensional vector in color space. It rotates in the adjoint representation like an 8 vector. So unlike in QED, where the electric and magnetic fields were observable, in QCD they are not. Chromoelectric and chromomagnetic fields are 8 vectors in the color space that are not themselves observable. QED, E and B fields are physical or observable. Not so in QCD. You can make a gauge transformation that basically scrambles up which color is which, maybe even shuffling around parts of the electric and magnetic sector. So you can define gauge invariant combinations of these things, but they are not gauge invariant separate. So finally, putting all the pieces together. We have the QCD Lagrangian. It's just the sum of those two pieces, psi bar I capital D slash minus M psi minus 1/4 F mu nu A, F mu nu A. This is deceptively simple. It's nice, however, because this term is separately gauge invariant. Also, this term is separately gauge invariant. But it's deceptive because it hides the role of the interactions. If I expand everything back out, I have psi bar I d slash minus M psi. I have the usual minus 1/4 d mu A nu minus d nu A mu A times d mu A nu A minus d nu A mu A, exactly the free part that we had before, plus all of the interactions. One of the interactions was this one, psi bar gamma mu Ta psi A mu A. But there are highly non-trivial self-interactions of the gluons coming entirely from the gauge sector. This piece from the square of F mu nu, let me write it again. So this piece, since it's squared, now includes cross terms. It includes something which includes the derivative and something which includes that interaction vertex. There are many copies of the same thing, and if you exploit the anti-symmetry under mu and nu, anti-symmetry under A, B, and C, then you can get rid of the factor in front of it. That linear cross term is minus GF ABC A mu B, A mu C, d mu A nu A. That's the piece that comes from the cross term between the free part of the kinetic operator and the interacting part. You also have the square of the interacting part. That one comes in with minus 1/4 G squared F ABC F A B prime C prime A mu B A nu C A mu B prime A nu C prime. Very interesting combinations. You get a combination between spatial derivatives and the anti-symmetry there, and the anti-symmetry of the color factors. And you can also get something based on the anti-symmetry of two color factors. These terms are all of the complexity of QCD. This piece right here is just the quark-gluon vertex. This piece gives me quark and anti-quark produce a gluon. If that's all there was in QCD, nobody would be talking about it. This piece, however, generates the 3 gluon vertex. So this allows gluons to interact with themselves in a 2-to-1 or 1-to-2 fashion. This one enters at second order G squared, and it has 4 gluon fields in it. This is the 4 gluon vertex. The 4 gluon vertex enters with a very different structure than the 3 gluon vertex. The 3 gluon vertex has a derivative. When you apply that to a Feynman diagram, that means this Feynman rule is going to depend on the momentum p mu. That's the vector that this derivative is going to return. So the 3 gluon vertex is a momentum-dependent vertex, a so-called derivative coupling. The 4 gluon vertex, however, takes place entirely through the structure constants. There is no derivative and therefore no momentum dependence here. The mu and nu's in here all come in certain combinations of the metric tensor. That's it. So let me just wrap everything up here. This is the point that I was trying to drive towards. I'm glad that we made it here. Next time, what I want to do is write down the Feynman rules and do some simple calculations of an example process that will set us up for the discussion of small x. I want to calculate quark-quark scattering and then quark-quark scattering plus an extra gluon. And we'll see exactly where that resummation starts to come. Okay, thank you very much. Happy to take questions. Yes, sir.
So the gluon self-interaction was, and it came up because of the kinetic term, right?
Yes.
So now you're saying the 4 gluon vertex has no momentum.
Yes.
And
It's counterintuitive because in QED, this is a non-interacting part of the Lagrangian. and it's not non-interacting in QCD. And that difference is required by the gauge symmetry. If you tried to keep only the non-interacting piece, that's not gauge invariant. So you're forced into allowing the gluons to have self-interactions exactly of this type in order to create a pure glue Lagrangian, which is gauge invariant. They're very non-trivial how that non-abelian matrix structure gets translated down the line and forces the gluons to interact with each other. But ultimately, it just goes back to this picture. It's the fact that your color has a direction associated to it, which then really just simply means for QED, if I have an electron coming in and an electron going back out, okay, maybe that's not how I should draw the final diagram. If I have an electron coming in and then an electron going back out, how about that? It's still the same electron after as it was before. So it has charge -1 before, charge -1 after, so the photon that it radiated was neutral because there was only one direction of rotation. In QCD, it all comes down to just the fact that your quark can come in with one color like red, go out with a different color like blue. And that means that the gluon is charged. It must carry the difference red minus blue for the gluon. So this goes exactly back to color is a vector. It has directional information. And as soon as you have directional information, the gluon itself becomes charged. And the charged gluon means it must have self-interactions or it cannot respect that solution. Other questions? When's lunch? Yes.
There might be some in the chat now.
Oh, good question.
No question from the chat. Sorry, just.
Yeah, that's a good point. Anybody online have something they want to ask? Okay, if not, then thank you guys, and we'll pick it up from here next time.
Yeah, no, they are just they are happy about the lecture.
Okay. I'll be available for questions over Slack as well.
Yeah, so let me add a couple of an hour. Thank you. But no, these were great lectures. I was a little bit busy with organizational things, so I lost part of it. Too bad for me, but you should enjoy that and watch it again.
You have the videos.
Because it's 3 hours that packed a few things.
Yes.
So maybe just tell you a couple of things. If you're interested in the geometric interpretations, there is by now old book by Mikio Nakahara, who introduces all the geometry, parallel transforms, whatnot, in a compact way. So you don't need a 3 courses in differential geometry to get there. It's pretty decent. So if you like all the stuff, it's Mikio Nakahara and like gauge field topology and whatnot. So you can recognize the title. The other thing is all those color flows and whatnot on these graphical ways of doing group theory and color calculation of the color factor you may need in a diagram or another. There is an interesting set of lectures by Doug Schitzer. So you read Doug Schitzer. I think Doug Schitzer. Yeah. It's not a book, so this is a book. The other one was a book. These are lectures, and I'm not too sure they are available on by themselves. They were advanced graduate lectures done at the summer school in the Black Forest in Germany years ago, and they are collected in interesting books by Springer. And I'm pretty sure it's called Lectures on QCD or something like this. Something like that. It's a booklet by Springer. I happen to have one in my office, so you can ask me to use it. This came to mind. And we also have Matt and a few links here and there, hyperlinks. We also have a HUGS pedagogical page. How many of you are aware of the HUGS pedagogical page? Oh, thank you. You read my emails. Good. There is more stuff there as well. If you find something particularly useful, let us know. We can add that. There might be some different things around by now. So if it's a live collection, living collection of them. So this was one. Another thing, two things. One, there are available for you in a finite amount cool water bottles in the fridge over there. There's a little kitchenette. You can open the fridge, and there is a HUGS sign on the bottom, so you can take whatever you want from the HUGS shelves and drawers. And there are also some sodas, and there are also some whatever Gatorade or whatever it is, squeeze flakes. So you are free also to use them. They are finite when they are gathered, but there is more than we have more in storage than you see in the fridge. So that's it for you. Finally, we got a gift from the education department, Lisa, who talked yesterday. We have a few tote bags, I don't know how to call them, a few bags with another Gerard logo for you to pick up, and I will bring them here, you can pick them up. And I think I'm done. Otherwise, so enjoy your the rest of the day. Yeah, okay. At 1:30 we come back for some spectroscopy lectures. So we'll be at another side of
Alberto, are these the lectures that you were talking about?
Yes.